All right, today we're going to be looking at percentages that are associated with the normal distribution. And one big rule that we have is the empirical rule. And the empirical rule involves three percentages: 68%, 95%, and 99.7%. What the empirical rule says is that 98% of the data is within one standard deviation of the mean. So in this section of the graph right here, all in here, you always have 68% of your data, always. The 95 means 95% of the data is within two standard deviations of the mean. So if we go out two standard deviations in either direction, all the way across to there, so everything underneath here, all that is 95% of the data. So there's not much left over out here. Hopefully you can guess. 99.7% of the data is within three standard deviations of the mean. So if we go out to 3 and all the way over, so pretty much everything under the curve except for this little tail on either side, that's 99.7% of the data. So last class, we were talking about statistically unusual. And we said if anything's more than two standard deviations away, it's statistically unusual. Well, this shows us 95% of our data is inside there. That means there's only a 5% chance that you're getting data outside of that area. That's why it's statistically unusual. So let's see how we use this. Suppose a set of test scores for 50,000 students is normally distributed with a mean of 81 and a standard deviation of 2.5. What region of the graph would represent 23,750 below average students? So below average is going to be pretty key here. That's going to tell us where we shade. We're going to shade into this picture somewhere. What we need to figure out is what percent we have. So 23,750 kids out of the 50,000 students that took it. That gives us 0.475, which means it's 47.5%. Now, based on the percentages we had before, 68, 95, 99.7, seems a little difficult to get 47.5. So here, we could split this section of 68 into two pieces. We have this piece and we have this piece. How much do you think would be in each? Well, they've got to be the same amount, so each would have 34%. So we know from here to here, that's our big 68. So if we split it in half, there's 34% in each of those. Now, if this whole thing is 95, but this part in here is 68, that leaves this section plus this section has to be 27%. Those together. So how much would be in each section? This section right here would have to be 13.5. This section right here would be 13.5. All right, so let's go a little further. Out here is 95. If we go all the way out this far, that much is 99.7. So to be in this little section and this little section, we're left with 4.7. So how much is in each? 2.35%. Now if we know that everything we've filled in so far is 99.7, that leaves 0.3 for the outside. So there must be 0.15% in each of the little ones. Now that's a lot of percentages. Do you need to memorize 68, 95, 99.7? Yes. Do you need to memorize all these little ones? Not necessarily. Do you need to know how to figure out all these little ones from the 98, 99, or 98, 95, 99.7? Yes. So if you would rather memorize them and not have to remember how to calculate them, you should memorize these. If you're okay with just remembering how to figure it out, that's fine too. So we need as many sections as it'll take to get to 97.5%. We also know they're below average. Where's our average? That's our mean, which is right here. So we know we're shading on this side of the picture. How would we get 47.5? Well, this is the only one with a 0.5, so that's probably a good starting point. 13.5 plus 34 will give us 47.5. So we would shade in this section of the graph. Now, if this was an SOL question and you're doing it on the computer, each of these little sections that I broke it up into, like 1, 2, 3, 4, 5, 6, 7, 8 sections, each of these 8 sections, you would be able to click on it and it'll change colors. So if you wanted these two, you would click on those two and they'd change colors for you. All right, so let's look at a different type of question they might ask you. The lifespan of turtles in a particular zoo are normally distributed, which just tells you that you can use the normal curve picture that we have below. The average turtle lives 91 years with a standard deviation of 21.4 years. Shade the regions under the curve for turtles living longer than 48.2 years. So what we need to figure out is where does 48.2 fall on this graph. So we know the middle is the mean, which is 91. If we're going to get to 48.2, we know we have to go backwards. Each one of these is one standard deviation lower. So 91 minus 21.4 gives us 69.6, which would be our first tick mark. Then if we subtract 21.4 again, we get 48.2. So let's shade under the curve for turtles living longer than that. So that would be everything above there. And if you wanted to, you could keep labeling the bottom of your curve, but we don't need to for this one because we got to the one point that we needed. When you're coloring this, try to actually stay in the lines since you're not doing it on a computer screen, and it'll be a lot easier for you to stay in the lines than it is for me. Color every last bit all the way through the bottom. All right, so what percent is that? There's two different ways of figuring it out. We could either take 100%, because we know that's the whole thing, and subtract out these two little pieces, which from before we know is 2.35 and 0.15. And that will give us that there's 97.5% under the curve. Or we can say we know from here to here is 95% plus this little bit, so 95 plus 2.35 plus 0.15, which will also give us 97.5%. So either add on the little bit at the top or subtract off a little bit at the bottom. Both ways, mathematically correct. They work. All right, so let's talk about the SATs. SATs, you will commonly hear, and like when you get your PSAT scores back, you read that you were in the 40th percentile for math. Or you hear them talk about little kids, and this kid is in the 70th percentile for weight. A percentile is the percent below, which is actually what that crazy chart, this thing that I gave you guys, this shows us all the percents below a certain point. And we will get into reading this shortly. So, suppose we look at the scores for one component of the SAT. If 45,000 students took the exam with a mean of 528 and a standard deviation of 87, so we know we're going up or down by 87s, how can we determine what percentile a student who scored a 702 ranked? So we need to figure out where 702 is on this graph. We're going to do that by taking 528, adding 87, moving up. So we get 615, and then 2 up would be 702. So we want to know what percent is below this. Well, conveniently for us, that is the reverse of the total of the turtles. So it is still 97.5%. 0.15 plus 2.35 plus the 95 in there. What if a student scored a 680? 680 is not exactly a certain tick mark on this graph. So we need to find the z-score first. Remember the z-score formula from last class is x minus mu over sigma. So z would equal 680 minus our mean of 528 over a standard deviation of 87. And we would get that z is equal to 1.75 if you round to 2 decimal places, which is what we're going to use because the crazy chart uses 2 decimal places. So let's look at your chart, okay? And remember 1.75. The z-score is very important for the chart. So right now, I'm on the negative side of the paper. Our z-score was positive, so we need to go to the positive side of the paper. We want 1.7 on the left. That's where you look for the beginning of your number. And then we want the 5 on the end, because that was the end. So right there, this was 1.7 and 5 meet. So that is our percent, except for they write it in decimal form. So we need to multiply this by 100, which would be 95.99. Which would be the 96th percentile. And what that means is that somebody who got a 680 scored better than 96% of the other students, which is pretty good. So that's percent below. What if we want to know what percent falls in between? Now, 480 and 760 are not exact marks on this chart either. So we need to find z for both of them. So the z-score for 480 minus 528 over 87, and we need to find the z-score for 760. So our first one gives us negative 0.55, and our second one gives us 2.5. 6, 7. Now, we need to find the percents for each of these. Okay, so negative 0.55, flip to the negative side of the paper. Negative 0.55. This is going to be a lot harder for me to read because I don't see it all on one side. It's the middle white column right there. That's where negative 0.5 and 0.5 line up. So what percent does that give you? It gives you 29.12%. Now we need the percent for 2.67. Sorry. We go to positive 2.6 and the column for 7 is right here. What percent is that? 99.62. Now, what this is, wherever they fall in here, down here is 480 and down here is 760. 480, this percent that we got here, it's saying down here is 12.8%. This is saying from here down is 99.62%. How could I figure out just what's in here? Well, we could take this whole amount, subtract off this end that we don't want, and that'll give us how much is in between. So 99.62 minus 29.12 leaves us with 70.5% are in between 480 and 760. So a decent amount of students. What if we want students that scored better or above what we were given? So like, how much is up here? Well, let's look at this example. If we wanted to know the students above 760, we know how much is below. We know the whole thing's 100. Take 100, subtract that percent. So let's do it with 675. Step 1, find the z-score. We get that z is 1.69. So then we look that up on our chart. We go to 1.6. I believe the last column's 9. Should be 1.69. It's right there. So we know that 95.45% is below. That's below. We want better or above. So we do 100 minus 95.45%. And that gives us that there is 4.55%. But the question did not ask us for what percent. It asked us for how many students. So we know that there was 45,000 students that took the exam. We need to figure out what 4.55% of that is. So we take that and we multiply it by the decimal form of our percentage. So divide by 100. And that tells us that there was 2,048 students that took the exam. for our last SAT examples, we're given the percentiles, which means we need to change them into decimals. If we divide this by 100, we get 0.68. That's the percent. If we look back at our chart, percents are on the inside. So somewhere inside this chart, it says approximately 0.68. Make sure you're looking on the inside, not on the outside, which is the pretty blue teal on my screen. So 0.68, closest thing to it, is right there. That comes from a z-score of 0.47. So that leads us to have a z of 0.47. So that should equal x minus 528 over 87. So we got to solve this. Multiply by 87. We get that 40.89 equals x minus 528. Add this to the other side. And we're going to round up, because it's an SAT score, we're going to round to a whole number of 569. So someone who scored in the 68th percentile got approximately a 569 on their SAT. Now, 90th percentile would mean we're looking for 0.90 in the chart. This one's a little trickier, and I'll show you why. 0.90, somewhere in here, somewhere in here, somewhere in here. A lot of people think it's this one, because it says 0.9015. And the next one's 32 at the end. That's bigger than this. Technically, 89.97 is closer to 90 because it's 0.03 off, and this is 0.15 off. So the z-score associated with it would be 1.28. Now, if your z-score is off by 1/100th of a decimal, it'll be okay. I'll know what the answer is. If it's a type in your own answer on the SOL, you could have problems. So we're going to use 1.28 as our z-score. So 1.28 equals x minus 528 all over 87. Multiply both sides by 87 to get it out of the denominator. We get 111. 36 equals x minus 528. Add 528 to the other side. And we get x is equal to 639. Remember, we're going to round to a whole number because SAT scores are a whole number. If we were doing something with money or something like that, we could use a decimals. All right, last page, everybody's favorite. I know you guys love word problems. So the useful life of a radial tire is normally distributed with a mean of 30,000 miles and a standard deviation of 5,000 miles. The company makes 10,000 tires a month. What's the probability that if a tire is purchased at random, it will last between 20,000 and 35,000 miles? So we're given two amounts of miles, which means we have to find two z-scores. So 20,000 minus 30,000 is negative 10,000, divided by 50,000 is negative 2. 35,000 minus 30,000 is 5,000. Divided by 5,000 is 1. You can use your empirical rule to look this up. You can also use your z-score chart. If you look for negative 2.00, you get a percentage of 2.28%. And if you look for positive 1.00, you get 84.13%. And we want to know between, which means we have to subtract them. So 84.13 minus 2.28 tells us that there is an 81.85% chance that the tire will last between 20,000 and 35,000 miles. Now onto the farm. The weights of eggs produced on a farm are normally distributed with a mean of 1.4 ounces and a standard deviation of 0.4 ounces. To be graded extra large, an egg must be at least 2 ounces. This means more than. Has to be more than 2 ounces. What is the probability that an egg from this farm will be graded extra large? So first we need to find the z-score. We know if it's 2 ounces minus our mean of 1.4 over standard deviation of 0.4, we get a z-score of 1.5. Looking at our chart, 1.50, 93.32%. But since we want it more than 2 ounces, this is how much is below. So there's only a 6.68% chance that an egg from this farm is going to be extra large, so he should probably just stick to regular sized eggs. That's all for today. See